you know, sometimes can be a bit mistaken, and I want to break that term apart, show you some of the tools that are within it, and then show you a few example use cases of things that are kind of happening within that. Um, and one of the biggest misnomers, I'll get into this in a minute, is that you need to be running this stuff on the cloud to actually make use of cloud native geospatial, which is kind of far from the fact or the truth, I should say. And I was lucky enough to get added to the editorial board of cloud native geospatial. So one of the big challenges that we've started to face is to really start to help understand how this technology can really help, and understanding where it came from is probably the first key challenge. So that's where I'm going to start our presentation today. If we go here, so let me just do the spotlight feature here. So how did we get to this place where we need what we call cloud native geospatial? So let's start with this. Imagine you have a server, a geospatial server, just a regular server, and you have thousands or hundreds of thousands of satellite images. Like you're collecting massive amounts of data and it's all kind of sitting there, or you maybe have a really big, geodatabase full of vector files. But when you're looking for that data, you only need a small chunk of that. Either that's a small spatial extent or a small temporal extent. How should you start to filter that? And that was actually a real problem that uh, some folks were facing at a specific time. Like the traditional GIS workflow would force us to move and download massive parts of those files. I'm sure you've experienced this if you're trying to download, giant chunks of files from an open data server or something like that. Databases themselves, you might think, hey, let's move into a database, but that can get really expensive, especially if you're storing that data in memory, or a database or a server or you can kind of swap that out for any sort of geospatial technology. The key is that most of the time you're only using a fraction of the data, right? Unless you're doing a very extensive area that you're looking at, or in a very extensive, swath of time, that at that point you would need, to actually scale up and have some other tools to support that. But for the most part, let's say you're, looking and studying, Dallas or, the Dallas Fort Worth Metroplex, something like that. You don't need the entirety of the globe. And that's kind of the problem that cloud native geospatial actually tries to solve. And it's meant to help us to access very large, robust data sets, but only get the parts of the files that we actually need. And that's like if there's a big takeaway from today, that's probably it, is that cloud native geospatial is really puts a lot of power in the user's hands to retrieve only the data that you actually need to get access to. So what does that look like? And this all started actually at Amazon Web Services, or AWS, as I refer to it going forward, and Landsat. AWS decided to actually host Landsat data in their storage service, which is known as S3. It's called Simple Storage Service, or S3, or three S's. You can kind of get how they got to the name. And they started storing it there. All that is basically like a server in the cloud where you're dumping a bunch of files and it lives in a cloud, and then you can access those files that way. They ran into a big problem in that letting people get access to that was hard, right? People were going out and downloading large swaths of those files, and they might only need a specific pass of a specific date or a few specific dates, or they only need a few bands of the data. Landsat, I think, it's pushing like 20 something bands now, 18, 20. I can't remember exactly. But it has within that single raster data set, it has a ton of data that's embedded within it. So users didn't want to like download gigabytes of data for just a small chunk of data that they actually needed. And that's really inefficient. That's what we would call like IO kind of charges, or ingress or egress, which is basically you're paying to move that data in and out, and the cost is moving it over the internet, right? And that's a costly operation that we would like to avoid because it's for the most part unnecessary. So there's also these traditional limits like APIs we're not scalable. Like it's very hard to say like, oh, I want to, an API like Google Maps API or any other APIs that you might have used in the past. They're good for a one-to-one communication, right? That's when the API is designed for, is to say, take one bit of data, retrieve something back. For batch operations or downloads, it's really not the most effective system to do that. Databases as well will start to balloon in size, and it costs, tens, even hundreds of thousands of dollars to maintain something like that for a database. So it's just inefficient to do it that way. So that was where the new opportunity was. The cloud provided a way to make the files themselves smarter. And that's what cloud native geospatial does, is it embeds a lot of intelligence and data filtering and data processing into the files themselves. So here's what AWS did at this time. They built a data structure into the files themselves. So instead of putting all the data in a database where you could query or do a spatial intersection to say collect all this data in a bounding box, all of that logic is embedded into the file. And when I'll talk about the different file types that exist for cloud native geospatial, or at least a few of them. That's what that logic put in place. So you have a structure in the file, and instead of putting that in the database, it adds to the files. Now, cloud storage, that AWS S3, there's other types of cloud storage with Azure Blob Storage and Google Cloud Storage is cheap. And the good news is it keeps getting cheaper. So as these cloud services build out and compute infrastructure starts to scale up, that price has actually gone down over time. So it's not like something that gets more expensive, it actually gets cheaper. So that's a good thing. Databases, on the other hand, have to store data in memory, which means they have to have disk space plus the processing embedded in one thing, and that gets actually quite expensive when you scale that up. So that's what they did. There's simple access. You can actually access specific slices of data, and we'll talk about how that's in the file structure shortly, with a simple HTTP call. Now, an HTTP call might sound like an API call, but it's actually different because the HTTP call is actually passing a set of parameters over to the files and then retrieving that data back in bulk, right? So it's actually saying, it's sending in some information to the files and then retrieving that data back, or it's only taking bits of the data that you need, which is also another key advantage there. There's no infrastructure when you do this. You are querying or accessing the data from any number of tools, including desktop GIS systems, or you're accessing that from you could even access that from tools like GeoPandas or Raster.io and Python, DuckDB and other open source tools as well. But the key is that you're using those existing tools you already have as a part of your ecosystem, and you don't need an extra database to actually access this data. You don't need any cloud technology to access this data. You just need to have the right permissions to get access to it. And for the most part, this is open data, so it's very easy to get access to. The key here is that you're only downloading what you need. You're only taking the bits of the files you need, nothing more, nothing less. That saves you time. And these are very efficient file structures that we put into place. And that saves you cost because you are absorbing no cloud infrastructure costs yourselves. So that's another big thing. So here's another sample use case. I try to put these into context. Imagine you're a GIS analyst in Dallas, Texas, which some of you might be, and you want to study urban flash flooding. I've been kind of fascinated with floods recently because I live in New York. We've had some pretty significant flash flooding over the past several years. There's been some crazy videos of our subway system flooding. And actually, there's been some pretty strong negative consequences. Unfortunately, some people have passed away from that. Basements flooding, all of these different negative consequences. So flash flooding has been something that's been pretty interesting to me. And let's say you actually want to study this in a local system. And let's say the place is Dallas. You want to kind of model what stormwater flow would look like, and you want to use a high resolution elevation data set. There's an actual data set I've used for this called height above nearest drainage. It's a global raster data set that allows you to, in 30-meter resolution, get the height above the nearest drainage, which isn't the actual elevation, but your distance to a nearest drainage point, so you can see where water is likely to flow from there. That data set in total is about 996 gigabytes. So pushing a terabyte, not exactly a terabyte, but close to. Now, instead of downloading massive chunks of those files, gigabytes at a time to kind of get the right data that you need, with Cloud Native, you can actually over your HTTP request or over your call. And a lot of this HTTP request stuff isn't like code you're writing. It's actually now embedded in the user interface of some tools. You're just grabbing the the portion of the file you need. You can pass a bounding box and say, hey, I just need it in the bounds of this map view. I just need it for this date if it has multiple dates in it. And you can avoid downloading all of that data. In addition to that, other tools are also doing this in processing. So let's say you want to get the height above nearest drainage and perform a zonal stats join for every building in an area in Dallas. What you can actually do is only materialize the specific pixels over that HTTP request that you need. Rather than downloading the entire file, you can call out, retrieve the pixels, and pull those down. Once again, this is all happening on your local machine. The compute is on the cloud service provider, in this case, AWS, and you can scale that seamlessly from a small part of a city or even a single city up to an entire state, an entire country, or the globe if you wanted to. And that's really the magic of all of this, is that it's simple to set up. There's no cost absorbed to you. It's very scalable, and you can kind of scale and move this around as you need to. So one big thing is that it's not just for big data. Now, cloud native has been kind of synonymous with big data because it makes accessing big data very efficient, right? It does allow you to efficiently query that data or pull it down or do anything like that, but it's not just for big data, right? You can also allow it to provide scalable temporal data that you're collecting, and I'll showcase this use case in a minute, which is reading a shapefile over the web from NOAA. It's the US water model, and I'll showcase exactly what that looks like and how to add that and collect that data temporally, but do that updating every 15 minutes. It allows you to store vector data very efficiently. So you can pull in, things like census blocks or property parcels or block groups and do that without storing kind of massive vector files. You can really compress the file structure quite a bit. So your storage cost goes down, but it also has all that querying efficiency built into it. And you can pull satellite imagery scenes directly into ArcGIS or QGIS and do that on demand. And then these tools are already supporting that, which is really great for leveraging these ecosystems. So what are the building blocks of cloud native geospatial data? I'm going to actually open this whole thing up. We can kind of go from the bottom of the pyramid up. But the first one is the cloud optimized GeoTIFF, or COG, right? What a COG is basically it optimizes very large raster files. First, it splits them into tiles. So those tiles are usually 512 by 512 pixels. That's the normal, I should say. It's not always that way. You do have the ability to do that. For the most part, it's 512 by 512. It splits the world up, and then within that, it also creates overviews at different levels that it's going up. So let's say that you just want the average elevation for all of Dallas. Now, I don't want to analyze every single pixel that falls within the bounding box or the polygon Dallas, but if I have a higher level overview that stores an average or something higher, I can actually take that higher level overview and intersect or do a zonal statistics with less pixels, which means less time and less cost. So that's what that is. Those are really the two core data structures in a COG. In stack or spatiotemporal asset catalog, that allows you to actually do data discovery. So it really is paired with the cloud optimized GeoTIFF and allows you to do very efficient data discovery. So it's effectively a search tool that allows you to search for data in a specific time range or data in a specific area. And that allows you to do that. It also embeds some other pieces, but we can take a look at that. But stack isn't actually a file format. It's a catalog specification, which is slightly different. So I just want to call that out. If I say catalog specification, that's what stack is. Now, GeoParquet is one of the newer entrants. I think it's about maybe 1.5 or 2 years old at this point. I can't remember exactly the date, but it builds upon the Parquet file specification, which is a very efficient file storage format for analytical data. And analytics means large scale data or temporally dense data, which means data that's updating on a regular basis. That's tabular in format, so something you would expect in a database or Excel type structure. and it adds geometry support for that. Plus, there's a bunch of efficiencies embedded within that as well. So there's a lot of things that you can do, such as row groups. You can query based off of bounding boxes really efficiently, and only read parts of the data that you need. But I'll get into the weeds in that in a little bit. ZAR is building off of, if you've ever come across netcdf files, these are array-based formats. So this is generally climatology data that's collected at, let's say, like a resolution of 1 kilometer grids or 1 degree grids, like very large scale global climate data. Things that like air quality or temperature or stuff like that, but it's collected every day or every hour or something like that. So it's kind of this three-dimensional data. You have it across X and Y space and then across time. So this allows you to store that in an array-based data structure. If you're familiar with Python, that's something like a list, and allows you to slice and dice that list or that data cube, as they would call it, very efficiently. So it's called a multi-dimensional array. That's why we have that name. And then, oops, Apache Iceberg is the newest one here. That is a catalog and almost like a database structure that adds database-like functionality onto things like GeoParquet files that allow you to keep a history and record of that data. And I'll show you exactly what that looks like in a minute. So let's go through these in a little bit more detail. And any questions that you have, I'm trying to keep an eye, see if there's any questions, but feel free to put those in the chat or wherever those are. I know we're going to ask questions at the end, but if there's anything like, hey, I want to know that right now, just go ahead and add that as well. So cloud optimized GeoTIFF is really just a GeoTIFF. There's nothing different. It still ends in .tif or .tiff, but it includes a few things. There's a tile pyramid, right? So that's that structure that allows you to create these overviews of data. So there's the tiling the tiling splits it up into those grids, 512 by 512. Overviews, as you can see here within each tile. So here's the raw underlying data. If you can kind of see this, this drawing here, then there's overview 1, 2, and 3. These are effectively like zoom levels as you go up. And then at if I only need the data at overview level 3, I can skip going to the raw data, skip processing extra pixels, extra bytes, extra data, and just do that efficiently. And then each tile has metadata that's associated with it. So that's really what it is. It's like you can say, oh, well, I'm passing a bounding box that only affects tile 1, so I can ignore everything else in the data set. And I only need the granularity of overview 2 resolution. That's what that'll do. There's nothing you have to specify as a user to do this. It just does it automatically with all these querying systems that are built in. So to be clear, you get the benefit of this. It's just being built into the file. And if you go back to the origin story here, that might help make a little sense. So what does that mean for you as a user? There's no need to download the full raster. It works with existing tools like QGIS and ArcGIS Pro. It's great for aerial imagery, DEMs, elevation, or even land cover data. So there's an increasing catalog of people that are migrating to this type of data. So that will help with any raster data analytics that you might need to do. Stack, or the spatiotemporal asset catalog, does a few different things. So it's about how you can add discoverability to your cloud native geospatial data, or specifically COGS. So it acts like a catalog, which means it helps you discover things. So if you think of it like a table of contents in a magazine or a book, that's kind of how I would start to think about it. It'll tell you what the things are, where they are in space, and then when they took place. So it allows you to search across those different slices, like I just said, and it has advanced filtering. So it actually can filter scenes and say, I want images that have a cloud cover less than 10%. Or it uses this specific sensor or something like that. And then it works with great data sets, and specifically large data sets across time and space, like Sentinel or Landsat and things like that. So that's what Stack does. GeoParquet is the vector format of these. Now here is an image of what a GeoParquet file looks like. What you have here is these, it's basically a columnar data storage system. So if you see these little blocks that go up and down, this would be one column of data. So here's your index, here's some number data, here's some other data, and then here is your geometry at the end of that. So that's what you have here. Now, what's key here is that if you just need column 1, 2, and 5, And if you query those, it ignores everything else automatically. Because it's in a columnar data store, it doesn't have to loop over rows of data. It can just say, I don't need this, and I forget about it. And it has this nice little index here to reference that. On top of that, it has what's known as row groups. So if you see these big 3 circles or, circular rectangles, I should say, those are file groups, or sorry, row groups. Now those are chunks of rows that could be 5 rows, that could be 100,000 rows. And within that, it stores different data. On non-spatial data, like this numerical data here, it stores things like the count, the average, min, max, stuff like that. So if it says, I need to know about all 5, or in this case, these 4 rows, and I include every one of them, I can just take the whole of the row group and say, I'm going to skip, I don't have to analyze each row. I can say, I just need the average of these 4 rows. They match my query. Great. I can take that and say, that's the average. The same works for spatial data. If I know that everything in that row group falls within a bounding box, and that row group has a bounding box on it, which is another efficiency, it can just say, I need all of it. So grab it and pull it in. So imagine you are creating a bounding box for the entirety of the state of Texas, or you're actually pulling the bounding, or the polygon there. It can say, hey, this bounding box for this row group includes everything and it falls within the bounds of Texas. I need all of it. I don't need to analyze all 100,000 points within that. So there's a massive efficiency gain there. And then on top of that, you have the file metadata, which contains things about your geometry, CRS, projection, all that good stuff. So there's a whole, separate section there. So you get your vector data plus your speed of the parquet data, which is all of those additional efficiencies I mentioned. So you store your geometries, you have your metadata, bounding boxes, your projection system, stuff like that. That has optimized for filtering and spatial joins. So if I was doing a ST intersects or something like that, it's super efficient for performing stuff like that. And this works with a lot of modern query engines. 2 I'll point out is DuckDB and Apache Sedona. So DuckDB is an in-memory analytical database that you can run on your computer. You can run it with Python. There's a lot of easy ways to do that. Apache Sedona allows you to do that in distributed sending, to basically go out and spread that out across multiple workers. You can run it locally, you can run it in different systems, but it helps you scale up to larger data sizes and scales. So ZAR, as I mentioned, is that multi-dimensional array. So it's like a NetCDF. ZAR is kind of like just an extra layer that reads on top of that for things like climate data. Really, this is where it comes into play the most, right? Let's say you have, water temperature data that goes back to 1960, which there are data sets like that, and they measure it every day. You can actually fly all the way back to 1960 and then measure chunks of days and filter that data efficiently. It chunks that data and compresses it, just kind of like the row groups, very similar to that, but allows you for reading efficiently over the cloud. And then there's time series analysis. So you can slice time and region and only get the data you want. So if you see a commonality between all these file types I've talked about, it's the ability to slice and dice that data and just get the data you need. So that's like I said, that's your one thing you walk away with today about cloud native geospatial data. That's what you should know. So what are some of the tools that work with this? Inside the Esri ecosystem, ArcGIS Pro supports cloud optimized geotiffs directly, so you can do that. Notebooks that you can use alongside of GeoPandas or Rio X-Ray, which is an extension of Rasterio that can expand your options if you're using ArcPy and things like that. You can work alongside these files with S3 data from AWS or Stack endpoints, which I can show you a little bit about. Or you can actually use DuckDB in Python to read inside of ArcPy or ArcGIS Pro. You need to know a little SQL to work with that, but it's actually fairly simple to spin that up. It's just a Python package. Outside of Esri, GeoPandas, Rasterio with Rio X-Ray, DuckDB, Apache Sedona. Those are just a few of the tools that sort of support that. A lot of them are in the Python ecosystem. So that's a big part of this is side of the Python sort of ecosystem. You can work with this inside of PostGIS. There's lots of other tools that are increasingly supporting this, GDAL, things like that. But usually I find people accessing these inside and reading them inside of Python. So that allows you to do that. So you can integrate them with modern kind of workflows or open data portals and stuff like that. Now, the last thing I'm going to touch on is Apache Iceberg, and I'll show you exactly what that does in a minute. This is something that we've been working on at Whereabouts, is actually to bring geospatial support to Iceberg. Now, all of these things, cloud optimized GeoTIFF, ZAR, GeoParquet, it's just files, right? They're read optimized, but they're not versioned. And you don't know if you make a change to them, an update, a delete, or anything like that. A database has that complete history embedded inside of it, like even like an Esri server or something like that. What do you do there? So Iceberg adds table level metadata. It's actually just a very small thing. It's just a small file, a JSON file that treats all of those files as tables, right? So if you think of a bunch of Parquet files that are dumped in a single folder, that now reads as a single table, which is a big advantage. Plus, it has the history that's embedded. So if I do an insert or an update or a delete, I can write it just like I would a SQL statement, and it will manage that for me. So that's the big thing. There's inserts, updates, upserts, deletes, all of those data operations you want to perform. And the biggest cool thing about this is time travel. Now, I don't mean this literally, but if I wanted to say, go back to a version of this table from 10 minutes ago, or from 5 days ago, or from a year ago, it stores all of that for me. I have a current version of the table, which has the current rows, but I can actually fly backwards and see what that is. And it has audit trails. You can see who updated it. There's conversion control to say who gets access and who can insert or update or delete. All of that stuff's embedded in that. So it's what we would call a geospatial lakehouse. This is probably a term you'll start to hear more especially if you're working with distributed systems. But a data lake is just some different files and stuff like that. But then there's also a bunch of different things that are coming with like a lake house, which adds the data warehouse like functionality for time travel and stuff like that. Okay, so let's walk through a real use case and show what this looks like in practice. So one data set, and like I said, I'm very interested in floods lately. NOAA publishes data from river gauge sensors across the entire country every 15 minutes, right? It sends it to a shape file. There's a .zip you can download from the NOAA website, and that updates every 15 minutes, but it overwrites the last one. So there's no history. I can get the current view of that, and that's great. But what if I wanted to know the history that happened before that? So I can't unless I store and work with that data myself. The next is first thing I want to do is convert that to GeoParquet. So I want to pull that into efficient format and then eventually store that in Apache Iceberg and then create a history. So I want a queryable archive of everything that's been happening. So we can't get a historical record unless you work and implement a workflow like this to have that historical record. So that's actually a use case I'm going to pull up here and showcase that and go through there. So why should you, and I understand you're working across a lot of different use cases and workflows and tools and sizes and scales of projects and geographies and things like that. Why should this matter to you, right? First of all, is that if there's these very large data sets that are hosted on the cloud, and you can start to pinpoint these data sets, who has Stack, who has cloud optimized GeoTIFF, who's using GeoParquet, you can start to analyze these very large data sets and bring them into your workflow without changing the core tool you're using or accessing. Like I said, you can use ArcGIS, you can use QGIS, you can use Python. Bring that data in with just a few lines of code, right? All this stuff that's happening benefits you as the user, right? Unless you are planning on producing and developing very large scale data sets, you just get the benefit of using this as a user. So that's a big, big, big advantage. So you can use your familiar tools, like I said. You don't have to leave Esri behind. So I sometimes, especially when I post content on YouTube or LinkedIn, it can sometimes seem like I'm like saying, throw Esri out or anything like that. That's definitely not the case. I think that what's really nice is that with all of this stuff we're building, you can use that in these ecosystems that already exist. Right. So that's a big, big component. You don't have to change your workflows dramatically to leverage this stuff. So most importantly, query, don't download. I'll show you how to access and query this data and leverage those things efficiently. I'll show you it through a UI and then some of the tools, like I said, you can use in Python to access that. But use the built-in optimizations in the files to query the data, just the data that you need, and pull that into your system and go from there. And then build for the future. Like you can actually help scale these workflows out to make them sustainable over time. Like if you build an analysis and suddenly you need to do the same thing all the way across the state or in a different country or in a different state or wherever, it's very scalable just to change your area of study and effectively replicate what you're doing without much hassle, right? So that's a key here, is that you can do this very repeatably and scalably. So with that, I can kind of show you a few different use cases and showcase what this looks like. So the first data set I mentioned was this height above nearest drainage, right? And this is a classic case of a very large data set that might be, it seems like it's difficult to access. It's asking you to, sign in with AWS and explore that. But I want to point you here. Let me see if I can use like one of the annotation features so I can, it's okay. So I'll just try to circle with my mouse. Down here, so if you see here, I have Stack 1.0 endpoint and via Stack browser. So if I want to go in the Stack browser, this is just a user interface that helps me visualize what's happening with the Stack API. And right, remember, this is the catalog. All of this is the cloud optimized geotiffs. So what's showing me is that the entire spatial extent of this data set is the world. So you can see that here. And then these are the individual tiles in that cloud optimized geotiff, right? And you can see if there's more information about the source. If I want to query the API directly, I can do that up here. Generally, you're going to be querying this via Python with that Rio cog or Rio Xarray or Rio cog file Python filter. But these are the filters that you have access to. Now, this data set was produced one time, so it's just timestamped at 2010. So it was produced at that specific point in time. So the temporal extent is a little less important. I'll show you one with the temporal extent, but the key here is like, filter by spatial extent. So let's say we want to look at data right in Dallas here. And this is the spatial extent I care about. I can hit submit, and it's going to filter and tell me this is the tile of this cloud optimized geotiff that you need. And here you can see that I can actually show this on a map. Here's the actual tile that covers that area. It'll help you visualize that. And there is a visualization piece to this with those tiling systems that actually makes it very efficient to visualize if you do need to do that. Otherwise, in here, you can actually just download this if you want. I think the whole thing is like, 65 megs, so not that bad. But that's what's happening. You can do this programmatically with Python. So there is the ability to just grab this data that you need and download that. So I've gotten that. I've taken that one chunk of file. This is the exact workflow that you can do to go from 996 gigabytes down to just the data that you need. So that's kind of what's happening with the cloud optimized geotiff behind the scenes. You can also just leave this on the server and query it remotely. So there's tools in QGIS to do this, and there's tools in ArcGIS Pro to do this as well. So you can actually just do some things like zonal stats and stuff like that. So that's another key option there. Another one that's kind of more interesting to look at. So we'll go with Landsat here. So same thing, there's a Stack catalog here. I think this is what it looks like on the back end. So it describes the data set and has all these different things in here. Let me see if I can get this on a Stack browser. And let's see here. Oh, so that's just the API. Let me see if I can find the right one. Landsat, had it open earlier today. And we can search here. And oh, this isn't the right one I was looking for. Okay. So this one I don't know where I found it before, but what is nice about that is that you can actually have some filtering. Let's see if I can find Sentinel here. Maybe it was Sentinel 2 I was looking at. So what's nice about these is that you can also do some filtering here by the cloud cover. So within this filtering, if I can go in here, sometimes it should have the cloud cover percentage. And then within the API, you can actually do that. Now, there's a nice extension in QGIS that if you want to test this out, I don't know about the one in ArcGIS, but you can actually say, hey, I just want cloud cover by a certain percentage and stuff like that. So you can actually filter it there. So jumping into the other use case, this is the US water model data. Now this data is updating every 15 minutes, and I'll just do a quick refresh to find that. And you can see here, based on the legend, that most things aren't flooding right now. but there are some in some different flood states. Some are minor or action, which means it's sort of starting. So you can see actually that there's some flooding down here by Port, just north of Port Arthur. So we can actually open this up, and you can see here that there's a history. This is updating every 15 minutes. You can see here that there is actually a history that goes back over time um, that you can see in the map view. But to collect this data and analyze it, like you can actually just grab it yourself and do that. But you can see here it also has these forecasts that are updating future forward. So you can actually see those and you can get a view of this flooding. But this is kind of data that you would actually want to get and maybe historically analyze, right? This is something that would be interesting to do that. So the data is here. You can actually download this data as a shapefile. Let me see if I can find the files here. And I think, yeah, right here. So this is the data that you can actually get to. You can see here it's on a basically like a public FTP server, or you can download with the links here. You have the observed water files, which is the current one. And then these are the forecasts here, which is you can kind of see national water model. Oh, that's not the right one. Shape files. You can see here that's updating kind of every 15 minutes. So this will re-update in 15 minutes and go from there. But what I care about is collecting a historical record and actually doing something with that. So that's what I did to actually build that out. So to do that, I built a notebook in Whereabouts. This is our platform to do that. I created a compute environment, medium size. I clicked open up, and then I created a workflow to do that. So it does a few different things, and basically establishes a connection to my cloud storage, which is just my user, my S3 path. And then this is creating that database in Iceberg. So I can actually do that. And I can loop over all of those files, which I've created a pipeline to remotely download them. So I've downloaded them, I've extracted them, I've done that whole thing. And then I just create a new table here. Now, what's important to look at, if I'll zoom in here, is this, that I'm, for each data frame, reading in the shapefile, just loading that in from storage. I'm looping over that entire set of data, and I'm telling it to overwrite, right? So I'm saying overwrite that table, which you would normally think is just completely overwriting it. The old data goes away. With Iceberg, that's not the case. I get a complete historical view. So what's nice is that I can actually say, and I'll get rid of this line for now, is to say, show me the current view of this table. So this is my current, I have to restart my compute. Hold on, it times out every 15 minutes to save on cost. So once I establish my compute connection to Apache Sedona and Whereabouts, it will say, here's the current view of this table, which is the current structure based on the latest data I pulled in. So I'm pulling that in. Just to show you what I'm doing here is I'm creating a job to do this in Apache Airflow. So this pipeline is running. It has 4 steps. I get credentials to ingest that into my S3 bucket, so it's secure. I extract the files from the web server and unzip them in that process. I then load those unzipped files up to S3, and then I run my my test here to actually complete the process that you're seeing in the notebook. So that's what's happening here. So all these things are running concurrently. It's scheduled to run every 15 minutes. You could, this is very similar to doing this in like an FME or some other tools that allow you to do some different scheduling and things like that. So you can tell me, here's my next run. It's going to run at in 5 minutes, and I'm tracking all of this on the back end. And I can see if there's any errors or anything like that, if that took place, or if there's any problems as well. And then same on the back end here, I can see all of my runs and see exactly what's taking place. So you can see here it's been running in the background as we've been talking and going through this discussion. So what's happening, what's really nice here is I'm going to query this, and I can see here for the current time, I can actually filter this and write a query. So if I just wanted to say where state equals Texas, and we can go status equals action, I can do that. And you can see that there's none in the action state right now. Let me see. I have to capitalize status. That would probably help. Or maybe that's not the right one. Let's see here. And you can see here that there's some of these that are out of service or not working, but this is the current slice of this data. And what we can actually do now is, let me see if that's, I can actually grab that timestamp and say, go back a few. This is in Universal or UTC time, so technically it's in London time, but I can actually go back and filter this for this specific timestamp and say, even though I was overwriting the data, I can go back a few steps and say, what was it previously? Now this is taking it from a few hours ago, about 2 hours ago. I can actually go back in history. Now, what's nice is that the table is still the table. I don't have to like filter this. I don't have to keep a long table. The current table is the current view, but I have access to this entire history. So I can go back and forward, see all these time slices over time. So this whole process, there's a few different things. I do some data structure where I add like an array to show the forecast and stuff like that. So there's a few different steps here that I'm filtering the data. And then ultimately it ends up, and I perform a getus org star analysis here at the end. So I'm just performing that spatial analysis, and then I'm pushing that up to my WebGIS here. And this is updating and running every 15 minutes. So I have my current sensors here. I can see the current view of this data. So this is all the flood sensors. These are the ones we were looking at before, just north of Port Arthur here. You can see it's it was in minor, so that's why I wasn't seeing it. It was in action. And you can see the view here. If there's any forecast data, sometimes there is, sometimes there isn't. You can see the flood height that I've had to manually calculate. So it's at 2.29 feet above what it should normally be. So here's the observed level of that. And I can see that for the entire country. I've filtered out ones that have no flooding. If I do want to see those, I can show those as well. But then I also have my spatial clustering analysis on top of that to say, okay, given all of the ones that are any bit above what it should be, here's where you can see some potential flooding. Now, the darker colors are less likely to be flooding, but these lighter colors certainly indicate that there is some flooding in this area, or there is some significant flooding cluster that's taking place. And this is updating without my intervention. It's running in the background. And what's great is this is actually a really massive data file because I'm collecting this every 15 minutes. So it's about 10,000 to 13,000 rows, depending on how many sensors are in service at any given time. We can check the original map to see what that looks like. But I have that complete history, so I can go back in time, I can go forward, I can have that ready to use and updatable at any time. So I can kind of get a complete view of floods as they take place, which wasn't available before. And it's all just stored. If you want to see what this actually looks like on the back end here, I'll zoom out, go to storage. And you can just see here in data, I have my rivers, and this is just the current forecast data. And you can see here, it's just stored in very efficiently compressed GeoParquet files. And then I have my complete history stored in my metadata, which is here. And anytime I make an update, it just changes the metadata under the hood. So this is my complete history, just files, just GeoParquet. And eventually I can make this available to anybody to query as open GeoParquet data with the iceberg catalog. You can see the history, and then anybody can have actually access that. So that's the goal, is to really start to make this very accessible across many different systems. So I think that was the goal, was to hit about 45 minutes, which I think we hit here. I just wanted to make sure that we were on time, first of all, and then to see if we had any questions from the group here.
Feel free to raise a hand or drop your questions in the chat.
We did have one comment. Liz Parrish said, "This is such a great presentation. Thanks so much for presenting on this important topic. Getting smarter about data is always a good thing."
Good.
But no questions so far.
Okay, see. Oh, one question. Do you want me to read it, or it doesn't matter to me?
You can go ahead.
Question is, what do you think is the biggest hurdle researchers face when transitioning to cloud native geospatial development? I would say first is that it's primarily been code-based right now. I think that it requires using some tools in Python It's usually like the fastest approach, or in SQL. So if you're used to a desktop GIS, those tools are just kind of starting to trickle down, but ArcGIS is supporting those, and QGIS is as well. So you can certainly view stat catalogs in QGIS and actually download data that way, or in ArcGIS as well. And then to actually query the data, that's where I think I'd like to see more development actively happening, that you can actually run or query these cloud native data sets and take advantage of that built-in data structure directly from the desktop without you having to kind of like do any of that, right? So for example, in that height above nearest drainage data set, just to test how much data I could push through, I did a spatial join, joining every building footprint from the world from Overture Maps data, which is something like 700 million buildings or something like that, with that entire raster data set, doing a spatial, like a zonal stats to say what's the average height above nearest drainage for this building with a small buffer around it. So that's what I did. And it works because Whereabouts is built on a scalable cloud compute. What I'd like to have happen is to say, if you have a couple of buildings in your, the area of interest that you're working on, that should automatically take advantage of those same things, because you're only materializing the pixels within that small area. So if I only need 3 pixels from the entire tile, I take those 3 pixels, get rid of everything else. This whole process is built to say less data transfer over the top. So that's one area I would say is difficult, is making that switch. If you're actually building these files, there's a whole other track that I usually go down to say how you do that efficiently. And I'm working on some content to build around that, but that's one thing. What's the primary